Welcome to the lecture series on CFD, Part 1. This is Lecture 5 on Advanced Finite Difference Methods. In this lecture, several advanced finite difference methods will be described with hints how other higher-order methods for the approximation of first and second derivatives can be developed. In addition to Taylor series expansion and polynomial fitting methods described in Lecture 4, compact schemes of fourth and higher orders will also be covered. I'll also explain how deferred correction approach can be used to implement compact and higher order approximations in implicit solution methods. In this way, both memory requirements and computing effort for high order methods can be significantly reduced, thanks to the fact that outer iterations are required anyway because of the nonlinearity of transport equations. At the end, numerical experiments are conducted to check the order of various approximations of derivatives. In Lecture 4, derivation of approximations for first and second derivatives using polynomial fitting was described for second-order methods. If we want to derive an approximation of a higher order, we need to involve variable values at more neighbor nodes than just the left and right neighbor I plus 1 and I minus 1. By fitting the function to a polynomial of degree n, we need to determine n plus 1 coefficients. Therefore, we need to fit the polynomial to variable values at the node I and n neighbor nodes. Fitting a polynomial of an uneven degree requires an uneven number of neighbor nodes around node I. For example, by fitting a cubic polynomial to variable values at 4 nodes, we can choose 2 nodes on the forward and 1 node on the backward side, or the other way around. On a uniform Cartesian grid, the following expressions are obtained for the forward and backward approximation. These approximations are called third-order backward difference and third-order forward difference, respectively. They are both third-order approximations. This will be confirmed by numerical experiments in slides 14 and 15. Polynomials of even order require an even number of neighbor nodes on either side of node I. They lead to higher order central difference approximations. By fitting a polynomial of degree 4 to variable values at 5 nodes on a uniform Cartesian grid, we obtain the following approximation. This is a fourth order central difference approximation. Using the same approach and polynomials of a higher degree, approximations of any order can be obtained. High-order methods involve more neighbor nodes and thus require more memory and longer computing times than methods of second order, which refer only to nearest neighbors. Implementation of boundary conditions is also more complicated, as will be demonstrated in Lecture 6. We mentioned earlier that the second-order central difference approximation is an average of first-order forward and backward approximations. The fourth-order central difference approximation is also an average of third-order forward and backward approximations, as can be easily verified by adding the expressions for the latter from the slide 4 and dividing the sum by 2. In polynomial fitting, one can use both variable values and its derivatives at certain grid points to determine coefficients of the polynomial. A compact fourth-order scheme is obtained by fitting a polynomial of degree 4 to variable values at 3 nodes, I plus 1, I, and I minus 1, and derivatives at 2 nodes, I plus 1 and I minus 1, which is known as fourth-order Padé scheme. This is the expression for a polynomial of degree 4 centered around node I, and this is the corresponding expression for its derivative. Because we are looking for an approximation of the derivative at x equal xi, we only need to determine the coefficient a1, because all other terms in this expression become 0 at location x equal xi. By forcing the polynomial to function values at nodes I plus 1, I, and I minus 1, and its derivative to derivatives at nodes I plus 1 and I minus 1, we obtain the following 5 equations with 5 unknown coefficients, a0 to a4, when the grid is uniform with a spacing delta x. To obtain the coefficient a1, we subtract the third equation from the second and add the fourth and the fifth equation to obtain the framed system of two equations with two unknowns, a1 and a3. We need to determine only a1, so we multiply the first equation by 3 and second by delta x, and then subtract the second equation from the first to eliminate the terms containing a3. At the end of the procedure described in the preceding slide, we obtain the following expression for the first derivative at node I as a function of variable values and first derivatives at nodes I plus 1 and I minus 1. In the case of a non-uniform grid, a contribution from variable value at the node I would also appear, and the multipliers of each value would be functions of grid spacings between the grid nodes involved. The above expression can be rewritten as the second-order central difference approximation plus a correction which raises the order to fourth. We shall see in slides 12 and 13 how this fourth-order approximation can be implemented in implicit solution methods using the deferred-correction approach. A family of central difference approximations up to 6th order can be expressed as follows on a uniform grid. The values of the coefficients alpha, beta, and gamma, as well as the corresponding leading truncation error terms for the second order and fourth order central difference schemes and fourth and sixth order compact Padé schemes on uniform grids are given in this table. Note that the leading truncation error term for the compact fourth order scheme is smaller than for the standard fourth order central difference scheme. The multiplier of the fifth derivative is smaller in this case. A compact fourth order approximation for the second derivative can be obtained following the approach used to derive the fourth order compact scheme for the first derivative, described in detail in slides 6 and 7. The difference is that in addition to fitting the polynomial to variable values at nodes I plus 1, I and I minus 1, we fit the second derivative of the polynomial to second derivatives of phi at nodes I plus 1 and I minus 1. This is the polynomial expression, this is the second derivative of this polynomial, and this is the second derivative at node I. Because at node I we have x equal xi, we only need to determine the coefficient of a2 to obtain an approximation for the second derivative. I skipped the intermediate steps because they are similar to those presented in slide 7 for the first derivative and show only the final result given by this expression. The expression for the compact fourth order approximation of the second derivative shown at the end of the previous slide can also be rewritten as the second order central difference approximation plus a correction to raise the order to fourth. This is useful when implementing this approximation in implicit solution methods, as will be described in the next two slides. If the same polynomial is used in the classical polynomial fitting approach to force it to variable values at 5 nodes from I minus 2 to I plus 2, we obtain on a uniform Cartesian grid the following fourth order central difference approximation of the second derivative. The same approach can be used on non-uniform grids as well. The coefficients in this expression are then no longer integer numbers, but functions of the four grid spacings involved. Higher order approximations lead to a larger coefficient matrix in the linear algebraic equation system if variable values from all grid nodes participating in approximations of derivatives are treated as unknowns. This requires more memory, the programming is more complex, and solving the algebraic equation systems requires more complex solvers and longer computing times per grid point and iteration. Some higher order approximations, like compact Padé schemes, cannot be directly implemented in an implicit solution method. It is therefore customary to use the so-called deferred-correction approach. A suitable lower order approximation is used to build the coefficient matrix, and the difference between the higher order and the lower order approximation is added as an explicit correction. The underlying term is computed using prevailing values from previous iteration and added to the source term. Because outer iterations, that is the update of coefficient matrix elements and source terms, are required anyway when solving nonlinear equations, this lag by one iteration usually does not slow down the convergence too much. However, it reduces the computing time for the solution of linear equation systems, that is inner iterations, drastically, which more than compensates for a slight increase in the required number of outer iterations. The all term can be programmed either as the difference of complete approximations of the derivative by the higher and lower order schemes, or one can write the higher order scheme as the lower order scheme plus a correction and program the correction as an explicit deferred correction. For example, the fourth order compact schemes for the first and second derivative can be written as the second order central difference approximation plus a correction as follows. The underlined terms are fourth order corrections to be computed using prevailing values from previous outer iteration. We repeat here numerical experiments presented in lecture 4 for higher order approximations. For this purpose, I have written a small computer program which computes numerical approximations of derivatives at x equals 0 on systematically refined grids using variable values at grid nodes taken from an analytical function. The same function as in the previous lecture is used, phi equal cosine of 3.2x minus 0.1. This plot shows graphically how the function, its first derivative and its second derivative vary between x equal minus 1 and x equal plus 1. Discretization errors are computed by comparing the approximations of derivatives obtained using the exact values of the variables at grid nodes and the analytically computed derivative at x equals 0. We first check the third order backward, third order forward, fourth order central, and fourth order compact Padé approximation for the first derivative on uniform grids. The figure on the left shows the exact value of the first derivative at x equals 0, 1.006613, and the variation of numerical approximations by third order backward difference, denoted by BD3, the green line, third order forward difference, denoted by FD3, the blue line, fourth order central difference, denoted by CD4, the red line, and fourth order compact Padé approximation, denoted by Padé4, as the spacing between grid nodes Tx is reduced. All approximations converge monotonically toward the exact value, except for backward difference on the coarsest grid. Now the curves for all schemes cannot be distinguished from the line representing the exact value when delta x is smaller than approximately 0.1. The plot on the right shows the variation of the error with grid spacing on a log-log scale. Backward difference PD3 and FD3 are obviously third-order approximations because the slope of the line asymptotically becomes equal to 3. That is, when the grid spacing is reduced by 1 order of magnitude, the error is reduced by 3 orders of magnitude. The fourth-order central difference approximation, CD4, converges with fourth order. That is, when the grid spacing is reduced by 1 order of magnitude, the error is reduced by 4 orders of magnitude. Even for a medium grid spacing, the error from CD4 approximation is more than an order of magnitude smaller than the error from third-order approximations. The most accurate approximation is obtained from the compact fourth-order scheme as suggested by the comparison of leading terms in the truncation error shown in the table in slide 9. For the medium grid spacing of 0.1 meters, its error is 2 orders of magnitude smaller than errors from third-order backward and forward schemes. I only cannot explain the behavior of the compact scheme when grid spacing becomes very small. Once I find the explanation, I'll post it. Let us now compare the convergence of two higher-order schemes, third-order forward difference FD3 and fourth-order central difference approximation CD4, with two lower-order schemes considered in lecture 4, first-order forward difference FD and second-order central difference approximation CD2. The first-order forward difference approximation results in high errors which reduce very slowly, linearly proportional to the reduction of grid size. For grid spacing of 0.01 meter, the error amounts still to 5%. The second-order finite difference approximation results in moderate errors which reduce 2 orders of magnitude when grid spacing reduces 1 order of magnitude. It is thus much more accurate than the first-order forward difference scheme. For grid spacing of 0.01 meter, the error amounts to less than 0.02%. The error from CD2 is even smaller than the error from FD3 for grid spacing larger than 0.2 meters. The third order forward difference approximation starts with errors larger than with CD2, but it quickly attains the slope 3, and for grid spacing of 0.01 meter, the error is below 0.001%. The fourth order central difference approximation starts with a similar initial error as CD2, but because of its fourth order error reduction rate, its error for the grid spacing of 0.01 meter is below 3 times 10 to minus 6%, which is far lower than engineers would ever need to go. If we aim to reduce the discretization error below, say, 0.1%, with CD4 we reach the goal with a grid spacing slightly higher than 0.1 meter. With FD3 we need grid spacing around 0.05 meters. With CD2 we need grid spacing around 0.02 meters. And with FT, we need grid spacing below 0.001 meter. When we consider grid requirements for a three-dimensional flow simulation, this means that FD3 would require almost twice finer grid in each direction than CD4. For CD2, the ratio is over 4 times, and for FD, over 100 times more grid nodes in each direction than CD4. Let us now examine the performance of two fourth-order approximations for the second derivative. Central difference approximation, which fits a polynomial of degree 4 to variable values at 5 nodes, see slide 11, and compact approximation, which fits a polynomial of degree 4 to variable values at 3 nodes, and the second derivative to derivatives at 2 nodes, see slide 10. The figure on the left shows the exact value of the second derivative at x equals 0, and the variation of numerical approximations as the spacing between grid nodes Tx is reduced. Both approximations converge monotonically and rapidly toward the exact value. After the third refinement, the curves for both schemes cannot be distinguished from the line representing the exact value. The plot on the right shows the variation of the error with grid spacing on a log-log scale. Both schemes are obviously fourth-order approximations, because when the grid spacing is reduced 1 order of magnitude, the error is reduced 4 orders of magnitude. However, I cannot explain why for the smallest grid spacing the slope reduces. I try to find the explanation and also check the behavior for other functions, polynomials and trigonometric functions. Finally, we want to compare the convergence of the fourth-order central difference approximation, CD4, with the second-order central difference approximation, CD2, which was presented in Lecture 4. The second-order finite difference approximation results in moderate errors, which reduce 2 orders of magnitude when the grid spacing is reduced 1 order of magnitude. For grid spacing of 0.01 meter, the error is smaller than 0.01%. The fourth-order central difference approximation starts with a similar initial error as CD2, but because of its fourth-order error reduction rate, its error for grid spacing of 0.01 meter is about 5 times 10 to minus 6%, which is far lower than engineers would ever need to go. If we aim to reduce the discretization error below, say, 0.1%, with CD4 we reach the goal with a grid spacing slightly larger than 0.1 meters, while with CD2 we need grid spacing of around 0.03 meters. When we consider grid requirements for a three-dimensional flow simulation, this means that CD2 would require 3 times more grid nodes in each direction than CD4. This is a brief summary of the lecture on advanced finite difference approximations. Higher-order approximations of first and second derivative can be easily derived for uniform Cartesian grids using polynomial fitting. The same goal can be achieved using Taylor series expansion. On non-uniform grids, the coefficients are not integer numbers but functions of grid spacing. For CD4, one has to solve a system of 4 equations with 4 unknowns. It is usually both computationally more efficient and easier to program higher-order methods using the so-called deferred-correction approach. In numerical experiments, it was confirmed that BD3 and FD3 converge with third order and CD4 converges with fourth order. Because the analytical solutions for the derivatives were known in these numerical experiments, it was possible to compute the exact discretization error for each grid spacing. CD4 and its compact version were in all cases the most accurate schemes tested.